In the second part of the tutorial, we will discuss a bit about the monitoring procedure, and then we will see a number of application of the logic to different scenarios. In particular, we will see three different scenario, one considering a static space and a regular grid, where we study the formation of patterns. Then a scenario with a static space and a stochastic system, where we study the availability of bike in a bike sharing system. And then one with a dynamic space, where we're going to describe the connectivity and reliability in a wireless sensor network. Until now, we designed just offline monitoring algorithms, and similarly as STL, STREL has two semantics, a Boolean semantics that tells at each location and time step the Boolean satisfaction of the property. So as for STL, we have a spatial Boolean signal S, such that the signal is in location L at time t is equal to 1 if and only if our space model and spatio-temporal trajectory in location L at time t satisfy the property. We don't have as STL is all one value for the whole spatio-temporal trajectory, but we consider a spatial Boolean satisfaction that correspond to the satisfaction at time 0. So given a spatio-temporal trajectory, we can give as answer the whole spatial Boolean signal, all the spatial Boolean satisfaction at time 0. Then we have also a quantitative semantics, where we have evaluation of the satisfaction. And in this case, so we can have a spatial quantitative signal that give at each location and times units the value of the robustness function for our spatial model and our spatio-temporal trajectory in position L and at time t. And similar, we can define the spatial quantitative satisfaction that correspond to the satisfaction in each location at time 0. So what we have in all is as input we will have our spatial configuration, just one configuration. If we have a static space or a dynamic configuration where you have a different graph for each time unit, and a spatio-temporal trajectory. Then we have a specification, our formula, and given this we have, computing the monitoring algorithm, we have as a solution a spatio-temporal satisfaction or a spatial satisfaction. So as for STL, the monitoring algorithm work on parse 3 on the tree of the formula, where we have at the bottom our spatio-temporal trajectory, and then at each nodes correspond to a sub-formula, so to a specific operator of the formula that we are considering. And then we have a different algorithm for each operator. So what we have done mainly is to extend the evaluation even for the temporal operator to spatio-temporal trajectory, and then in particular we add the algorithm to check the spatial operator. Just a consideration about the computational cost for the temporal operator. We are using algorithm like the STL monitoring algorithm, and they are linear in the length of the signal times the number of location in the spatial model. Instead, the spatial property are more expensive, and they are based on a variation of the classical Floyd-Warshall algorithm. And the number operation to perform is quadratic for the reach operator and cubic for the escape operator. As a first example, we consider a scenario with a static space and a regular grid. We want to study the formation of pattern. To do that, we consider a reaction diffusion system that describes the production of skin pigments that generate spot in an animal force. In particular, there are two proteins that diffuse in the space and react with each other when they are in a connected cell. Here you can see in the video the evolution in time of the system, and you can see that after a certain number of time units, there is a spatial configuration that is stable in time, where there are a number of spots in the space that are almost equidistant from each other. And here we see just the evolution in time of the concentration of the protein A, where in the spot, so in the blue part, the concentration of A is very low, and in the red part, the concentration instead is high. As a space model, we consider the regular grid, and we treated that it as a undirected weighted graph, where each cell of the grid is a location, and we consider to have edges between connected cells, so between cells that are neighbor in all four directions. And we consider to have only one label which corresponds to the Hopf distance function, so that is equal to 1. So if two cells are neighbors, then the distance is equal to 1. The spatial-temporal trace describes the concentration of the protein A and B in each cell of the grid at each time step. And this is generated by a reaction diffusion system that we discretize according to a finite difference scheme as an ordinary differential equation, where the variables are exactly the cell of our grid. Okay. As first property, we want to describe the formation of the spot. We can use, to do that, and probably you will guess it, the surround operator, because it works very well to describe regions that satisfy a certain property and that are surrounded by another region that satisfy a second property. So we can describe the formation of spot using this formula. That means eventually, in a time between 19 and 20, so in the time when the system stabilizes, it's always true from that time that this property is satisfied. That means there is a region where the location where I'm checking the property belongs, where A is always less or equal to 0.5, and that region is surrounded by another region where all the nodes that belongs to that region satisfy the property A greater than 0.5. Furthermore, from the region, the location where I'm checking the property, all the location of the first region should be at the distance less than W2 from the location where I'm checking the property, and all the region of the second, all the location of the second region should be at the distance between 1 and W2 from the location where I'm checking the property. If you remember, we say that we are checking the property in each location. And here we can see the solution that correspond to the satisfaction at time 0 in each location. So on the left, we can see a snapshot of our system of the concentration of protein A in each location at time 50. In the center, we can see the Boolean satisfaction, and on the right, we see the quantitative satisfaction. In the first line, we consider a distance constraint W2 equal to 6. Instead of the second line, we consider a W2 equal to 4. So you can see in the Boolean satisfaction, the location that satisfy the property are the location red, and the location blue are the location that do not satisfy the property. You can see that in the first line, almost all the location that correspond exactly to the spot, so to the blue part on the trace, on the snapshot on the left, satisfy the property. Instead, on the second line, you can see that if we restrict the bounding constraint, if we restrict the distance constraint, then almost the only location that satisfy the property are the location in the middle of the spot. And sometimes even there are some spots that are missing because they are not very regular, and so no any of its locations satisfy the property, the distance constraint. Instead, on the right, you can see the quantitative satisfaction in each cell, and in the color correspond to the color of the legend. So the maximum value where the property satisfy is anyway very close to 0, and this is because we are using just the protein A, and here we are considering one property that should be less than a certain value, and this property greater than the same value. Okay, here, so in the previous slide, we have seen a local property to define the spot, but what we would like is something to define the whole pattern. A way to define a global property using this operator is using the everywhere and the somewhere operator. So we can describe the whole pattern with this property. That means everywhere. So in each location, from each location should be true that from that location I can find a location at the distance between 0 and 50 where the property phi spots formed, so the formation of spot property, is satisfied. So this means that each node in the grid should be connected to a node at a distance less than 50 where the spot property holds. And the 15, so this value corresponds to the maximum distance between the spots. So in this way, we can describe a global property. Why? Because the everywhere operator, without a distance constraints, permit us to cover all the location of the grids. And the solution in each location will be the same. So it's enough for us to see one location and see the satisfaction in that location to know that this will be the same in all the locations. Here we can see 3 different patterns that we can derive from the same reaction diffusion system, changing the diffusion constants. The first one is the ones that we have seen before, and that permit us to have a pattern with the spots. If we change just a bit the diffusion constant, we can have very different patterns as the one in the middle, and some similar but with a bit different kind of spots as the one in the right. If we check this property on these different spatio-temporal trajectory, we can see that only the first one satisfies the property. Instead, if we check just the formation of spot property, particularly the last one has several locations that can still satisfy the property. With this last property, we would like to show you how we can nest temporal operator within spatial operator. We are considering here a perturbation property. To do that, we have perturbed our system. So we have considered the same reaction diffusion system, and instead to take totally random initial condition for protein A and B, we consider as initial condition the value of protein A and B at equilibrium. So when there was the formation of the pattern. And then we perturb just the value of one cell that you can see here in red, from a very low value to a very high value, higher than the maximum value of all the other location of both protein A and B. So that means that it was the only location with the value greater than 10, greater or equal than 10. And why we have used such a high value? Because to perturb the system, but also because in that way, as you can see now on the property, the only location that can satisfy the property the value of A greater or equal to 10 is the one that we have perturbed. So the property that we are considering is this one, where in the first part there is this atomic proposition, and if you remember, we are going to check then the satisfaction of the property at time 0. So the only location that can satisfy this property is for sure the location we have perturbed, because all the other has the value that is less than 10. And then for sure it is the only one that can satisfy, but it should satisfy also the second part. The second part, we are using again the surround operator, and this means phi absorb surrounded by phi no effect at the distance between 1 and 2. What does it mean this? So the first part, the property phi absorb, that means eventually in a time between 0 and 1 is always true between 0 and 10, then the value of A is less than 3. So this means that in one time unit we want that the value of our cell 6 is already going to less than 3 from 10. So we already want that most of the perturbation is already absorbed. And the second part, the property no effect, means that this means always between 0 and 20 that the value of A means should remain less than 3. It used to be sure that the perturbation remains confined inside the original spot without going out. Okay, so here we can see the evolution in time of the trajectory, and you can see that the perturbation is easily absorbed and by the system and is not going out from the spot. Indeed, if we check the property is satisfied by the trajectory. As a second example, we consider a scenario with a static space and a stochastic system. STREL can be applied on stochastic system considering methodologies as statistical model checking. Statistical model checking combines simulations of the stochastic system. That means an algorithm that samples the trajectories according to the probability distribution of the model um, with different possibility. For example, we will see in this case that we describe the system considering a continuous time Markov chain. So the statistical model checking combine this simulation of the stochastic system with stochastic model with a monitoring routine for the property feed, the ones that we have seen before, not the single trajectory. So the idea is that a stochastic system, a stochastic process can be described as the set of the all possible trajectory that it has. So the trajectory space. And on this is defined a probability measure on a certain sigma algebra of the trajectory space. This is something that we cannot compute exactly. So what we have is an approximation. So we cannot compute exactly so we cannot find exactly the fraction of the trajectory space that satisfy the property. But as we say, we can do it for a subset of this, where we check a subset of the trajectory space, and then we approximate the satisfaction probability. That means the probability that a trajectory generated by the stochastic process satisfies the formula phi. In a similar way, but we are not going in detail, just think that in a similar way we can define a robustness distribution with respect to the quantitative semantic instead of the Boolean semantics. So for example, if you think to the beginning of the just the deterministic integration or the deterministic result of the numerical integration of the infected recovery individual system, the epidemic system. If instead of the deterministic system we take a stochastic system, we will have a number of trajectory. We can compute for each of them the value of the robustness, and then we can see the frequencies of this. This will give us an approximation of the robustness degree. We consider a bike sharing system. A bike sharing system is composed of a number of bike stations that are distributed over a certain geographic area. And each station has a fixed number of bikes and of bike slots. And the user can pick up a bike, use it for a while, and then return it to another station in the area. We consider the bike sharing system of London. That is a very big, large bike sharing system. We have more than 700 bike stations, each with 20-40 slots, and a total population around 60,000 agents. So that are the users that can pick up and return the bike. From that, we model it as a population continuous time Markov chain with the time-dependent rates, and to fit the parameter of the system, we use historic journey and bike availability data. And the model, so given the number of bike free slot in a station at a certain time t, what he can do is to compute the probability distribution of the number of bikes and free slot in the next 40 minutes. So he can predict the evolution of the system for around 30 minutes, 40 minutes. The spatio-temporal trajectory corresponds to the evolution in time of the number of bikes and free slot in each bike station. And instead, the space model correspond, so we have as location the bike station. So the set of location L is the set of bike station, and the edges describe the connection between each station. And we say that two nodes are connected if they are at a distance less or equal than 1 kilometer. So if their Euclidean distance is less than 1 kilometer. And this corresponds also to the value of W of the label in the edge. So what we would like to check is the availability of bikes. And the idea of this property is to give the possibility of the user to consider if in the place where there is no bikes, to know if there are some bikes in some close station. The property that we want to consider is this one. Always true, that these two properties should be always true at each time step. The first one means somewhere at the distance between 0 and D, the number of bikes is greater than 0. With weight, we have the distance function that we have seen at the beginning that just compute the sum of the value of the weights. And I didn't see before, but the W, if you have seen in the formula, the W that we have in each label corresponds exactly to the Euclidean distance between two different stations. In the second part, we have the same, but instead to have to have at least one bike, we ask if we have at least one free slot. So we are asking both to know that each bike is never full and never empty. What we are changing, that we are going to see now, is the value of D. So this is the distance where we are going to check if we have a station where there are at least one bike and one free slot. So what's the idea? The idea is that at time 0, when D is equal to 0, what we are checking is just the location, is just the station that where we are checking the property. So this will be just, it's always true that in the location that we are checking, there are always at least one buy and one free slot. And as you can see, there are many stations that do not satisfy the property. This figure that you see here approximate the satisfaction probability for 1,000 runs. As you have seen, we are considering a stochastic system here, so we cannot check just one trajectory, but what we are doing is to take a number of runs and to do the average and the approximation. And we can see that anyway the standard deviation is really low. So here you can see the value of the probability satisfaction that goes from 0 to 1 in the legend, and the location red are the ones that do not satisfy the property, that have a probability equals to 0, and the one blue are the one that are always true in all the runs. So the first one is with d equal to 0, the second is with d equal to 100 meters. You can already see that we have less, so we are increasing the location that satisfy the property. And things are much better already with the 300 meters. That means that from each location, doing just 300 meters, in almost in all the location you have a probability at least greater than 0.5 to find a bike. And with the 600 meters you can see that all the location has at least 0.5 probability to find to satisfy the property. In this figure we can see the evolution of the satisfaction with respect to the distance of some specific location, and you can see that around 0.5 all the spatio-temporal trajectory and all these location satisfy the property, where this dot line is the standard deviation of each for each location. As last property of this example, we are adding something to the previous property, because if you think the previous property was just considering a spatial property that should be always true, but that means that a certain user you could know that at that time where the property was checked, there was some station with a free bike and free slot, but for sure it needs a certain time to go from his position to that station, and it could be that in the walking time that he's arriving there will be no more bike or no more slot. So for this reason we add to the property a temporal part nested. So instead to have just that from a certain location it should be always true that a certain distance there is a free bike and free slot, we are saying that from a certain location it should be always true that eventually at time tw the number of bikes should be greater than 0 and the number of free slots should be greater than 0. So we put together this the facts that we want that there are free slots and at least one bike, but this can be also treated in a separated way since maybe some user needs just one of the two. So this was just to make a global description with one property. So what is this TW time? This corresponds to the walking time to go from one place to the other, and it depends on the different distance that we are considering. So we are considering in this case an average walking speed of 6 kilometers per hour. So that means that if we are evaluating a distance of 0.5 kilometers, then we are considering a walking time of 6 minutes. The result of this of checking this property over our bike sharing system give similar results of the previous property. So that means that in that case, for the things that we have chosen, there is no much difference between looking at time 0 or after the walking time. As last example, we consider a scenario with a dynamic space. So this is similar to what you have seen at the beginning. So we are considering a sensor network, but it's a bit more complicated. So in that case, we are considering a mobile ad-hoc sensor network, and this system can consist of thousands of mobile devices that are connected, and that are using to monitor different things as pollution or temperature, humidity. And each sensor is equipped with some data processor or embedded battery. And this sensor can move independently in the space in any direction. And for that reason, they can change the links and connection with respect to the other. So in this system, we consider so we have three different type of sensor. There is the coordinator that is represented here with blue, this one, and is the unique node that is like responsible to initialize all the network. And then after this, it behaves as a router. Then there are the router that are this one, and they are like the intermediate between the coordinator and then the end devices, and they are passing the data between all the devices. And then there are the end devices that are the one in yellow, this one, and they can communicate only with the coordinator and with the router, and is enabled to relay data from other device. As you remember, we have seen two different possibility of graphs considering this sensor network. And now you are seeing the evolution in time of the connectivity graph. And now you see on the right instead the evolution in time of the proximity graph. You have seen when you have very few nodes, the connected graph can have many nodes that are not connected. Instead, the proximity graph is always connected. All the nodes are in some way connected in the space. If you are considering much more nodes, you can see that the situation is different, and is the connectivity graph that has much more connections. Instead, the proximity graph will remain always with the same proportion of connection. The SASP model consists of, as a location, the devices. So the set of location are the set of devices. And in that example, so in the next slide, we will see properties that are considering just the connectivity graphs. But if you are interested in see other property or example, please contact me, or you can ask me during the question and answer time. So here, considering just the connectivity graph, we say that there is an edge between two locations if and only if the Euclidean distance between the two locations is less than the minimum between of the two communication range of Li and Lj. As spatio-temporal trajectory, we consider the evolution in time so the temporal signal in each location of three variables. The node time that actually is a constant in that case, the level of the battery and the level of the temperature. The node type is 1, 2, 3 to denote the coordinator, the router, or the end device. Anyway, in the property we will write directly coordinator, but in the implementation there is the node type. So actually the codomain is the integer set times real set times real set. In the first property, we're going to specify a connectivity behavior of our system. In particular, we want to specify that an end device is either connect to a coordinator or can reach it via a chain that of at most 5 routers. The reason why we are checking this property, we are specifying this property, is because we say that the end device should be directly connected to a router because it's the only one that can share information with it, and it should reach at a certain point the coordinator, because the coordinator is the one that starts everything. So we want that the device is connected to a router that should be connected to a coordinator, or the device can be directly connected to the coordinator. This can be described by the free-connect property that specified the property device reach in maximum 1 hop a location that satisfies this property, so that is a router, reach in maximum 5 hops a coordinator. So this is satisfied by a location that is a device and can reach a location that is a router, or can reach a coordinator in maximum 5 hops, where in each hops it should satisfy the router property. One problem that can be this property, that can have this property, is that maybe we are not sure that this should be so it can happen that we have a connection that is broken, but the important part that is that this is always restored at within a certain time units, and this can be described by this second property, where so we add some temporal requirement that describe this fact that if you have a broken connection, this is restored within a certain time units. So we are asking that is always true, that if a connection is broken, this implies that eventually in a certain time the connection is restored. In this slide, we see the evolution in time of the Boolean satisfaction of the first property in the previous slide, so the one just with the spatial operator. In blue, there are the nodes that satisfy the property. Instead, in red, we have the nodes that do not satisfy the property. And since we have a property with just spatial operator, no temporal operator, then the length of the Boolean signal is the same as, so the final time is the same as the final time of the trajectory. As you can see here, we have a snapshot of the final time of the spatio-temporal trajectory, and we can see that the only node that does not satisfy the property is this, the L14, that corresponds exactly to the node, the only node that is just directly connected with the end device and is not connected with the routers or the coordinator. Another property that one could be interested in monitoring is the ability of the system to forward a message at a given distance. The ability of a component to forward a message is related to its, for example, battery level. And so one possibility is to consider this property. So from a given location, we can find a path of Hopes length at least 5, such that all nodes along the path have a battery level greater than 0.5. And this can be described with the escape operator. And we can say that the locations satisfy a property if it can escape with a battery level greater than 0.5 at the distance greater than 5. The battery level can be considered also for the reliability in a MANET. For example, we may also want to know if there is a path to the router which is reliable in terms of battery levels. For example, battery level above as again 0.5. This can be described by this property where we are asking that not just the router reach the coordinator, but it should reach a coordinator with the path where each router has a battery at that is above 0.5. Then we can consider instead just that the device should be connected to a router or it should be connected to a router that is connected to a coordinator. We can consider this reliable router that is connected to that it reach in one hop a reliable router. With this we finish the tutorial, the spatial-temporal property as some monitoring that I could show you. If you are interested, please contact me and we can see other possible applications that we have in mind. And furthermore, there is a tool. Moonlight is a Java tool, and actually in this conference it will be presented a MATLAB interface that you can use for specifying and monitor Strad property. And yes, this is the website. So that's it. Thank you to everybody, and see you soon to the question and answer session.